Good day to all of you. Today we shall study about modeling switched mode power converters. Though it is a vast topic and we will not be able to cover in just 1 hour, we will be taking more classes. We will start towards being able to model switched mode power converters. Today we will be discussing more on the modeling basics. So, that is why the title of today's lecture is called modeling basics. So, this is what we will be dealing in the major portion of today's lecture. Till now, you have been discussing DC-DC converters, the steady state analysis, non-idealities, and to some extent the dynamic models of the various isolated and non-isolated converters. We shall now look at how we try to control the switched mode power converter. You have looked at the switched mode converter as a open loop system. We need to control it, develop controllers such that we get outputs with a certain performance specification. So, that is the intent, and towards this intent we will develop the evolve the subject. Before we start even trying to control the switched mode power converter, we need to model them, the dynamic model, which you have been familiarized by previous lectures. We will dwell today in this class on trying to look at a generic way of developing these models and then apply it to the specific DC-DC converters. So, towards this goal, I would like to bring your attention to one important aspect in control system terminology. What is a plant? This plant is what you have been discussing in the previous lectures on DC-DC converters, but let us bring it into a format which is compatible for control systems design. It has an input energy port as shown here, very important. I am going to hash it. This is an input power port, energy port, wherein power is fed into this plant. You have an output from the plant, and we will call it as the output power port. These two are the major energy or power level ports in any DC-DC converter. The input is normally obtained from the input power supply, DC power supply, which has been termed as VG in the previous classes, and the output which is termed as V naught, having a voltage V naught. So, VG IG gives the input power, V naught I naught the output power. Apart from this, there are two other ports, not power ports, but signal ports, which you would already be familiar with. One is called the control input. Control input, it is normally given a symbol U, and the sensed or controlled output So, this controlled output has a symbol Y. So, internally this controlled output is generally linked to the actual power output by means of a sensing circuitry. So, this sensing circuitry does the function of capturing the actual power signal, converting it into a compatible low level signal voltage and giving it as a signal with which we have named it as Y. So, for example, in the case of a DC-DC converter, the output voltage, if you want to feed it back, you will be passing it through a device like an optocoupler or probably a Hall sensor, and the output of is signal conditioned and brought out as the controlled output signal, which is what will be fed back. So, with these 4 ports, a controller is generally designed, which is basically interfacing with the control input and the control output. Okay. So, the control process is generally linking these 2 aspects of the plant ports. So, this is our control ports process, which we will see what goes to make that up. Now, if we look at the case of a specific converter like the buck converter. Now, we know that the buck converter is of this form. We indicate the switches in this manner. So, the single pole double throw switches are replaced by 2 single pole single throw switches. You have an inductor, then a capacitor. So, this LC forms a filtering mechanism and followed by a load RL. Now, here at the input side, you have an unregulated or uncontrolled source VG. You have switch S1 and switch S2, and these are mutually exclusive in their switching. When S1 is on, S2 is off. When S2 is on, S1 is off, and you say that this is on for a period of time dt, where t is the switching, Ts is the switching period, and S2 is on for a period 1 minus d Ts, where d is the on time of S1 by Ts, the total switching period. So, to make it a bit more clear, if we say that time proceeds along this axis, and we have this much time allocated for the switching period T s, then we can say that this portion of the time where d is a fraction less than 1 less than or equal to 1, this fraction d T s and this fraction 1 minus d T s are the two mutually exclusive intervals of time during which time S 1 is on during d T s, S 2 is on during 1 minus d T s. Now, this particular circuit, if we look at this, how do we map this circuit into the plant configuration that we have been looking at. So, if we look at the plant, let us say that we have one input energy port, we have one output energy or power port, power output. So, what is the input and the output? So, if you look at this portion, this is the power input to the buck converter. So, that basically constitutes the input power. So, let us rewrite that as coming from here, and the voltage here is V g, the generated voltage, and the output you see is on this side, and we shall bring that out in this fashion. Where the output here is V naught and the load is connected external to this plant, because it is decided by not the plant, but it is decided by the user. Now, we have the input and output power ports. We need to define two more ports, which is the control input U, and another port which comes out of the plant, which is the controlled output Y. Now, what is the control input for this plant? We have seen the steady state analysis. V naught is equal to d times V g. Now, d, what is d? D is basically the fraction of the time the switch S 1 and switch S 2 is on and off within a period T s. So, D actually can be termed as a control input. If you reduce the value of D, then the output reduces. If you increase the value of D, the output also increases. So, therefore, the output in this case, which is V naught. So, if we measure the output voltage, signal condition it by passing it through appropriate optocoupled circuit, and then pass it on to the output port. So, V naught is the output signal, and this output signal can be controlled by an input, and what is that input? D. In the steady state, we say it is uppercase D. So, this D, which basically implies that you are in some manner trying to adjust the times for which these two switches are on and off. So, in effect it is actually one control input, because these two switches are directly coupled. They have only single variable D to control it, and they are mutually exclusive. So, in effect we have actually one control variable D, and that is what is brought out as the plant control input. So, if you see, this buck converter is mapped into a control plant block diagram, by saying that the control input is U, which in this case is D. This lowercase d is used to represent both variations plus steady state. There is a controlled output y, which is to be controlled, which in this case is V naught, and we have the power inputs. The power input being obtained from a supply V g, unregulated V g and I g being the input currents, and an output, power output, which is actually supplying a load I naught at a voltage V naught. So, this is our DC-DC converter, which needs to be modeled. Now, this DC-DC converter, a practical circuit, needs to be mathematically represented. Mathematically represented in a way which is amenable to develop the controllers. Now, the process of control is that we need to have a comparator and we need to have a controller. So, in the basic minimum, we need to have these two important components. This is the controller and a comparator. So, what is done with these two? So, the controlled output, which is sensed and then given as an controlled output signal, low power, low level signal information signal, is fed back to this comparator. Now, to this comparator, we need to also give a reference. So, it could be an output reference signal or a value, which is given as a positive or in phase, and to that reference we are subtracting the feedback signal to get the error. So, what you get here is the error between the feedback signal and the reference, and the objective of the controller is to give an appropriate value of control input, whatever be the control input D in this case, such that the error goes to 0. So, that is the job of this controller. So, this is what we want to ultimately achieve. So, in order to design this controller, we need to have a knowledge of the DC-DC converter in a mathematical form, and that representation is called the dynamic model. So, this dynamic model can be represented in two basic ways. The dynamic model the states space representation and the other transfer function representation. However, it may be pointed out at this point that when we develop the dynamic model of a physical system from the physics of its operation, we actually arrive at differential equations, a set of differential equations which are directly represented in this form called the state space representation. And from the state space representation, you can extract the transfer function representation. So, you could say that the state space representation is the one which you will first obtain and then convert it into transfer function representation for further analysis, or you could continue to do your controller design the state space representation itself. Anyway, first let us see how we will obtain the state space representation of the system. The system in our case is the DC-DC converter. So, in control parlance, the whole system including the controller and plant, controller plus plant, we generally call it as the system. The open loop uncontrolled part that we have here in blue is called the plant. So, keep that in mind, and let us proceed forth in trying to see how we can obtain the state space representation of a given plant. So, before we go into obtaining the state space representation of a DC-DC converter, because a DC-DC converter is a switched power converter. It has switches which are nonlinear in nature in the sense that they have two states. Superposition principle may not be directly valid. We shall look at a generic method for first obtaining the state space representation of a general cis plant, and then we apply it to the specific and special case of DC-DC converter. So, let us look at the case of a general plant, wherein we have a controlled input u and control input u and a controlled output y. I will not be writing this power input and the power output explicitly every time. It is understood that these two ports are there, but to make the discussion faster, these two will be understood to be present in the plant, and I will be using only u and y from the control point of view. These two are control signals, these two are only control signals, they do not contain any power, whereas these two are power signals. So, the job of the control signals is to control the flow of power in the power signals. So, even if I do not show these two ports, bear in mind that these two ports exist and they are part of the plant. Okay. It is only that I may want to draw your attention to this part while we are talking on the controller design or the controller portions. Now, let us say that we have a plant like this, a black box, we do not know what is inside, and the nature of the transfer curve, let us say input is on the x axis, independent variable, and the dependent variable y output is on the y axis, can be linear as shown like this. It could be in this fashion, or it could also be partly linear and nonlinear with a saturation. It is a nonlinear characteristic, or it could also have memory hysteresis, and various other characteristics. So, let us take a general nonlinear case and see how we go about trying to model the system. So, here I would like to mention that all the control signal analysis is done for a linear system. Analysis and design is done considering that the plant is a linear system. However, most of the systems are non-linear in nature, and therefore, we need to perform linearization. If we need to have an effective model of the plant. So, we will discuss these issues. Therefore, consider a general plant which is not linear, and let us say for this input output transfer curve, there can be various operating points like that. Let us say a specific operating point, let me shade it as solid, the specific operating point shown like that, and if it continues to stay in that specific operating point, then we say it is in the steady state, and we say the steady state values are uppercase values like this. Now, this transfer curve, as you see, gives you an idea of the operating point. This is the operating point. However, this transfer curve does not give an idea of the evolution, time evolution of the variables u and y, and you should note that both u and y are functions of time. Both u and y are functions of time. So, let us say for example, that we would also like to see the time evolution of the two variables, the input and the output variable. Let me put another graph oriented differently. This is u t along that axis, and along another orthogonal axis, let us say is time, and you project this value of u along. Now, for this operating point to have reached this stable operating point, it would probably have gone through these various intermediate operating points, overshot maybe, and then come back and then settled at this particular operating point. So, to see the time evolution, it probably may look like this. It may have started from 0, overshot the nominal operating point, undershoot, and then probably settle down to this, which will give this corresponding operating point as you are seeing there. Likewise, one could also have a time evolution of the output variable, the y variable, versus time on another graph with two orthogonal coordinates. And let us say if you are interested in seeing the time evolution, it may look like this, starting from 0, overshoots, undershoots, and then settles down at the steady state value as it is shown by this operating point, and this overshoots and undershoots all corresponds to these various points as shown here. So, this time evolution is the one which is of interest to us, and that is what gives you an idea of the dynamics. So, dynamics of the input and the dynamics of the output, and this is what we need to study and model such that these dynamics are taken care by the control input, which we are showing here. So, we need to control the way the time signals evolve with time and ultimately settle in the steady state point uppercase U and uppercase Y. And the design, of course, most of the time it is going to stay at the steady state point, and therefore, the design is done for the steady state operating point, which is what you have been discussing and studying till now in the previous classes. Okay. So, looking at this specific graph. So, let us say that we have U and Y input and output with the input output transfer curve like that, and let us say we are interested in a specific operating point uppercase U and Y like this. Now, this is a nonlinear curve. Superposition principle is not exactly valid for this particular curve. So, you have to treat it as a nonlinear system. The problem here is that designing and analyzing control of nonlinear systems is much more tedious and non-intuitive. So, most of the time the controllers are designed for linear systems, but then if the controllers are designed for the linear systems and the plants are nonlinear, how do they become compatible? So, we make a modification, something like this, we call linearization. We take a small portion such as this for deviations of U and deviations, expected deviations of Y. We have a small portion segment of the transfer curve, and this segment of the transfer curve can be considered as linear. So, if we say that the system is operating at this operating point, then deviations in the neighborhood of the operating point can be considered as linear, and the controller can address or take care of these deviations in the neighborhood of the operating point. Then a linear mathematical model and controller addressing the taking care of the small deviations in the neighborhood of the operating point can be designed and built. So, that is basically the approach that we will be using in building the controllers. Now, how do we go about saying that we have a linear model? Now, if you look at the generic model, you say the Y is a function of the input variable U. Now, this is the general model for the complete transfer curve, and therefore, we call it as a large signal model, because this model, even though nonlinear, handles the complete transfer curve U versus Y of a particular system. Now, for the specific case of the input U, uppercase U at the operating point, you get a response output which is uppercase Y, and that is called the model for that specific operating point which is in the equilibrium state, and this is called the steady state model. This is called the steady state model. Notice that in the steady state model, both the uppercase input and the uppercase response output, they are in equilibrium, they do not vary with time. They are constant with respect to the time, or the differential quantity would be 0. Now, let us consider the case the generic case Y, which is equal to f of u. We could use Taylor series and expand it about the operating point. So, we know that the output Y has to be Y plus or minus something, plus or minus some portion, which is given by the Taylor series as differential with respect to u, the function f, u minus uppercase u, the delta u, plus 1 by 2 factorial, second derivative u minus u square, all these evaluated at, all the derivatives evaluated at u equal to the operating point value, plus so on, keeps going. Now, if you take a very small deviation, that is delta u, which is u minus the operating point. If you take a very small deviation about the operating point and consider them to be linear, then we could say that because delta u is small, u minus u is very small, all second order and higher order terms can be neglected. Delta u square will be still smaller. We can take only this portion, and as we say that it is linear, the slope we can say is equal to a constant k. So, this becomes y becomes k times u minus, or y minus y steady state value is now this is the small signal deviation in the output, this is the small signal deviation in the input. So, the small signal deviation in the output, we will give it as a symbol y hat, and the small signal deviation in input, we will give it as a symbol u hat. So, we say y hat is equal to some constant times u hat, and this is a linear equation. This is the linearized small signal model of y is equal to f of u, which is the large signal model. So, you see that we have seen three ways of representing a particular system. Firstly, you have the transfer input output transfer curve, and this whole transfer curve can be represented as y is equal to f of u, and that is called the large signal model, because it handles the whole large signal of u and y. It can address that one. And then the equilibrium value, the operating point value is given by this y is equal to f of u. This is called the steady state model. It does not have any derivatives. And thirdly, you have the small signal model, which is basically in the neighborhood of the operating point. So, in the neighborhood of the operating point, we take a very small deviation about the operating point, and that small deviation is so small that we can consider that segment of the transfer curve as linear, and thereby have a model which is a linear model called the small signal model of y is equal to f u. Now, it is this small signal model which is used for designing the controller, and the controller handles these deviations, the small signal deviations. The steady state operating point requirement is met by separately by a feed forward value. So, for example, in the case of a DC-DC converter, you could say the input u comprises of a steady state value of duty cycle plus a small signal deviation in the duty cycle. So, the steady state duty cycle is a constant which is given directly to the open loop plant, and the controller output which handles the deviations about this steady state value is coming from the controller. So, the controller output provides these small signal corrections to the plant. So, this is the approach that we will be taking even for the DC-DC converter. Now, from this what we gain is that whatever may be the plant, linear or non-linear, the first step is to convert the plant into a linearized small signal model. So, it is this linear small signal model that we further use for developing the controller design. So, if you look at our controller, it would look something like this. Now, let us say we have a comparator, we have the feedback portion, you have a controller, as shown here, and the output of the controller is actually given as the control input to the plant. In this case, it is the duty cycle. So, let us say that at the plant I have an adder here, plus and plus, and to this you give the steady state D, and this goes in as D, and let the controller output give the deviation. So, this becomes d plus d hat, which is actually going into the plant and controls the output y, which is now small signal value V naught hat. So, out of the sensed signal from the actual power output, which is at V naught, this is having the steady state component V naught. So, let me write it in this following. The V naught is containing the steady state portion plus small signal deviations above the steady state. So, this is the one which is fed back here, and this is the one which is fed back here. And what should be the deviations? We want ultimately that the deviations should die down, should be 0. In the steady state, we do not want any deviation about the operating point. It should stay at the operating point, which means the reference for the deviations should be 0. So, if this error E is equal to 0, then this D would represent the D corresponding to the deviations, and this D represents the steady state value. Together they are given to the converter, and the power of course coming from the input V g. So, this is how the control block diagram will look like, and this is how we will try to attack the problem. So, we try to develop the small signal model for the converter linearized, and then try to see how we go about designing the controller. So, that being the main objective. So, in order to develop the small signal model of the controller, we adopt the following strategy. Any system, at least the power electronic systems, are composed of 3 basic or elementary components. Which is R, this is dissipative, second one we call it as the L, kinetic storage, kinetic energy storage, or current based energy storage. As you know that the energy is stored in half Li square by virtue of the current flowing through the inductor L. And third, another energy storage component called C, capacitance, which is potential energy storage component. This is actually a voltage based energy storage component. As you know that the energy in the capacitance is half CV square, and the energy is stored by virtue of a potential or charge within the capacitor. Now, these are the 3 basic components which are used in power electronic equipments, and to that we have one more component, which is the switch. So, switch is actually a nonlinear version of a resistor. A resistor has an I V characteristic which is linear, whereas in the case of the switch it has an IV characteristic which is nonlinear. So, when the switch is off, we have it along the x axis, and when the switch is on, we have the y axis as the operating points in this fashion. So, therefore, we need to address this component also, which is the switch component also, into our dynamic models, and how we go about doing this is what we will look at and study in the classes to come. So, to summarize now, what I would suggest now is that you get some practice on what are the inputs, what are the output, control outputs, what is the power output, and what is the power input of various DC-DC converters. What are the input variables, what are the output variables, what are the power in variables and power out variables of the 3 non-isolated converters, and the isolated converters like the forward, flyback, and the derived forward converters like the push pull, half bridge, full bridge converters. So, for these converters, get some practice in trying to phrase your block diagram in this fashion, so that it becomes compatible for controller design and understanding the controllers. And in the next class, we shall continue from where we left off today in trying to obtain the state space equations, the dynamic model for the DC-DC converters. Thank you.